Hello everybody, in today's video we're going to talk about work and energy with varying forces. Have you ever noticed that the harder you pull on a spring, the more force it takes? That's because a spring force changes based off of how much you stretch it. Unlike a constant force where the work equals to the force times displacement, we need to implement calculus to figure out the varying forces. And and we will go to an example demonstrating this idea of a graph. And we have a dem of a graph right here, but we'll open up a new menu. So we'll demonstrate this by drawing a graph with varying forces. So this will be a constant displacement with a varying force which goes up and up as displacement goes on. And we will start, and to find the work, you need to take the base times height, but because this is varying, we have to start by taking segments. So you take a segment right here, and we would call this dx, because this is a small part, times force. So you have dx times force, and then you take another segment times dx, and then you take another one. This is how you would do it if you would have a reasonable amount of segments, like for example, like 4. But to find out work, we would use work equals the sigma notation of force displace times displacement of x. And we get this from our original formula, work equals force times displacement. And you would sum up all these forces and the displacements that go along with this, so we can find the formula. And this is what will this what basically tells us is how we can find it if it's like a really small example. But now we will introduce the idea, because these number segments can be very large. We'll introduce the idea of integrals and finding work. We can see as the number of segments as become very large, the displacement in between each column goes towards 0, so you would be making like smaller and smaller columns as you'd go. And to find this, we would take the integral work equals the integral from x to 1. So for example, if x1 starts here till 2x2, which will end right here, x2, and this will be force times dx. Dx is just a small segment of x. And this shows us that we can use the integral to sum up the forces to find our total work, as the sigma notation and integral. All you're really doing is just summing up the displacements with the forces to find work. Now that we know how to find work with varying forces, let's take a look at a special case, which might seem a little bit familiar. And this case will be when force is constant, and this will agree with what we've observed previously. So you have work equals from x1 to x2 with force times dx, and in this example, force is constant, so we can just take it outside of the derivative since it's not. We can take it out if that was like 2 or 4, just like any constant number you would do in your integrals. And this would just leave you with dx. We take the integral of this will give you 1, or x, and you would plug in these numbers. You would get f equals x get x2, x1, and then you would plug this in, so you get x2 minus x1, which shows you your displacement in between to your maximum x2 minus the x1. And if we remember it, s is a displacement, so that means s equals the final minus the initial, so we can replace that with s. And this brings us to our familiar formula, W equals force times displacement. So you can see this agrees with our equation before in this special case. We will also draw a graph that agrees with this idea that work is when work is constant, we're actually finding the or when the force is constant, we're still finding the integral, but for example in this case, it's just base times height to find the area, which is the area under the curve, which is the work. So you'd have, for example, x1, x2, and then you would have a constant force, for example, at this point. And as you can see, to find the area, it's just base times height. This change of x, and then you're forced. All right, and we'll go to our next page. Now that we know how to introduce integrals, let's get into our application of finding the work with varying forces. Now we'll introduce Hooke's law when it applies to the idea of springs. When you stretch a spring over a displacement, we observe that the equation follows what we see. So you have a spring that starts here, and then you're going to displace it this amount of x value. So you would go from here. As you can see, the force equals this distance times whatever like resistance that the spring has, and we draw the formula as force equals this k value, this resistance to being pulled or compressed, times the distance. This is for short distances, and this k value, it's also, which is from Hooke's law, is also known as the force constant in your textbook. And we donate the units as Newton meters. Newton meters. Now and this kind of shows us how to find the work of springs, as the work equals force times whatever that displacement was from before. Alright, now let's apply this idea of integrals of varying forces to a spring, which will apply Hooke's law to. And as the elongation of the spring goes from 0 to a maximum value, we will find the work. And as you can see before, let's redraw a formula. Force equals the force constant times our displacement. This will look something like this. If we draw a graph, so we have our force as our function, and then x as our input, and as it goes up, we find that we have something that looks like this, and this will be our x1. We'll just call this x1 for now. And we have this area under the curve, which represents our work. We'll apply it as from what we remember from before. You write work equals the integral from 0, in this case, to x1. That's where we're going to be integrating to with the force times the dx. So each segment, we can draw it here to show you visually how we're going to be summing up all these columns times, and we're finding it by doing the force times whatever that segment was to get an approximation. But as we go infinitely towards zero of these columns, our calculation becomes more accurate. As you can see, that's how the idea works. So we take this integral. Right now, we don't have a variable x, but if we go back to our Hooke's law from before, we can get this into our formula. So we can write the integral from 0 to x1, and then we'll be left with kx dx. We can take this k out, but we'll just leave this here just for the sake of it. So you'll be left with k and 1 over 2 x squared from 0 to x1, and we know that just equals 1 over 2 k x. Actually, we should call this x2 2, and that's how we find this. But if you look at this, we can kind of just figure it out by looking at this right triangle here. We know that the area for a right triangle is 1/2 base times height. If you can remember from algebra from a long time ago, this result tells us that the work on a string is proportional to the displacement, rather than when work is constant, work just equals to the force times displacement when the force is constant. So let's get a practice problem so we can see an example, which is where this is being demonstrated. So imagine you have a spring. This is in its normal state, and it's not its normal state. Its normal state is 1 centimeter, or 1 meter, just to make it simpler. 1 meter towards to the left, and then someone pulls on it, which will bring it out all the way to x equals 0.3 in our case here. And the k value, or force constant, is equal to 200 Newton meters. How much work is done on the spring is our question here. So we can take the integral, or which we'll do to demonstrate what it looks like when the spring's already been pulled a bit. But once you remember the format, you don't have to do this integral every time. So we'll do from x1, from x2, and we have our force, which we'll replace with kx. As remember, this is force applied to a spring, so we can use Hooke's law, times dx, and this equals, right here, we'll take the k out this time, x with x1, x2 equals k times, oh wait, this is going to be x squared with over 2 times x squared 2 minus x1 squared, and we'll distribute that k value. So you have 1 over 2 k x squared 2 minus 1 over 2 k x squared, which is the first x. And as we can see, this is the format for finding the work when it involves a spring. So this is you can remember this, or you can do the integral each time, which either way, both are good ways. Remembering is good for tests if you want to be quick. Knowing the integrals is good so you can repeat your process however you like to do it. So now let's find our work. We know the final distance, we know the initial distance, and we know our constant force. The only unknown is our work here. So right now it's just a matter of plugging and chugging. There's no more physics here. So you have Newton meters with x. x2 is 0.3 meters squared. So this will get rid of this x, and then meters, and then multiply this will give you kilograms times meters squared over second squared, which is also represented as joules. So kilograms meters squared over second squared minus 1 over 2, our K value of 200 Newton meters, and then we have our initial displacement, which is right here. And now we will calculate these numbers out so we can know how much work was done. So you have right here, you have 9 joules minus, so 1 squared times 200 divided by 2, which would just give you 1 joule. So our work on the spring was 8 joules in this example, and that's how you find work under varying forces. Thank you for watching my video today. And if this helped you, or if you have any questions, don't forget to comment and like or subscribe if you want to encourage me with this type of content. And have a good day.